And so, welcome back to our Radiation Heat Transfer Learning Journal. In the last video, we were talking about the extinction coefficients and why it's important. Alright, so basically, we see that when radiation of a certain intensity enters a medium at some initial value, it will get attenuated. If we just consider attenuation and nothing else, it will just get attenuated, and at I lambda at this length s star equals to s, it will get attenuated according to this coefficient, the exponential of whatever this integral is here. Now this integral is basically, it takes into account both the length as well as the material characteristic of the medium. So the material characteristic of the medium is called the extinction coefficient, as we were discussing before. And this actually takes into account like how well the medium actually absorbs radiation. Okay, this quantity here. So this quantity is going to pop up very often, and it's a very important quantity to talk about. What do we call it? We call it tau lambda, otherwise known as optical thickness. This is known as optical thickness, right? So let's highlight it in green. Optical thickness, tau lambda. Why is it called tau lambda? Because this is extinction coefficient is based on a wavelength rather than a wave number or something else. In here, you find that the tau is based on the tau eta, right? Tau eta is the optical thickness based on the wave number, right? So why is optical thickness important? So let's say we have two mediums, both at, let's say, a 5 meter, right? Both, let's say, at 5 meters. All right, but the beta here is equals to 1. The beta here equals to 2. So while both the lengths are the same, and you have both the same radiation coming in at I lambda s equals to 0, s star equals to 0, but the thing is that the radiation coming here versus the radiation coming here, the radiation exiting here will be much stronger than the radiation that's over here, because this medium kind of absorbs more. Alright. However, if let's say we halve the length and we just get rid of this, and let's say this is now 2.5 meters. 2.5 meters. Alright. The radiation here and the radiation coming out here will be exactly the same. Okay. So why is this so? Because the optical thickness of this and this is exactly the same. So optical thickness is what really matters when it comes to radiation. It's not the exact length. So optical thickness is what really matters when it comes to attenuation of radiation, not the actual length, because you have to take into account how well this medium actually absorbs the radiation. So more often than not, you will see instead of us writing this integral again and again, you'll just put tau lambda at the top. Okay, tau lambda at the top to represent, okay, this integral, and this represents the optical thickness of this system. And now instead of us using ds, we don't quite like to use ds as much. Okay, we prefer to use d tau lambda or whatever d tau eta, d tau nu, that is what we would like to use instead. Okay, so usually when we come to radiation, we like to use this optical thickness to describe our systems. So you see tau eta is over here. Okay, so that's where we get our thing. So next thing in line is to describe augmentation. Okay, augmentation by emission and scattering. So we want to next describe the augmentation bit. All right, so what are the two things with regards to augmentation? That's the emission bit and then the inscattering. All right, so anyway, so how do we first we need to tackle first the emission bit. We need to tackle the emission bit first. So what is this emission? What is the emission bit? Okay, so let's do this equation again. The I lambda ds emission. So what is the contribution due to emission that changes this intensity? So according to the textbook, we use, there is this constant, this emission coefficient, noted as J eta, or for our case J lambda. Okay, let me go back, I think. Yeah, J eta. J, in this case I'll just use J lambda instead. And what is this? Okay, so they say at local thermodynamic equilibrium, the intensity everywhere must be equal to the black body intensity. Okay, I'm not going to go through that here, but suffice to say that after some derivations, which I'm not going to do here, we find that J eta or J lambda is equal to kappa lambda times IB lambda. So kappa lambda IB lambda. Now I'm not going to do a derivation of that, but at least I will try to help us get an intuitive sense of why this should make some kind of physical sense. All right, so emission is controlled by black body. I mean the black body temperature. I mean the black body radiation. So if a system is hotter, that means it should emit more radiation, right? So as we know, IB lambda is equals to pi times EB lambda equals to pi n square sigma t to the fourth. All right, if you still remember that formula, hold on, did I put it right? I think let's go back. I think a few videos back. Let's just double check whether I get it. I got the thing right. Scrolling. Okay, here we are. EB equals to sigma t to the 4. Okay, let me fast forward. Oh yes, IB equals to EBT over pi. This is what we have derived before. So let's go down and correct our equation, and yeah. So what this is saying is that the black body radiation is determined by this n squared sigma t to the 4th over pi, which should make sense. That's the maximum amount you can actually emit. Alright, and what is this kappa lambda here? What's this kappa lambda here? This is the absorption coefficient, right? The absorption coefficient of some sort, or the, yeah, this is the, when it comes to attenuation, that is what we have. Yeah. So this is the absorption, the same kappa lambda that we're talking about, and it appears in this this emission thing. So why is this here? So similar to a gray body, all right, that we have. I mean, the analog is this. We have kappa lambda. It talks about physical absorption of radiation, and it's very similar to the absorptivity, how absorptivity and emissivity are also very much related. So if we have a high degree of absorptivity, we will also have a high degree of absorptivity. We also have a high degree of emission. So that's why it appears in here, where you have a higher absorptivity, you have a higher emission as well. So this is what this equation is saying. Yeah, it does depend on the black body radiation coming out of thing, but as we know, participating media is not a perfect black body because it does not absorb all the radiation coming in. All right. In fact, it lets some of the radiation, transmit through the system. That's why it is participating media in the first place. Otherwise, it'll be a solid black body. And the degree to which it behaves like a black body is determined by this absorption coefficient, and that also affects the emission. So that's kind of an intuitive sense as to why this formula kind of works. Right, so hopefully this short explanation kind of convinces you that emission can be determined by kappa lambda into IB lambda, and we don't have to go through all the molecular derivations and such. So I'm going to just skip that part. That's in chapter 11 of this, but I'm not going to go too much into it. This is the radiative properties of molecular gases, which will describe why this is so at like the molecular level. So okay, so emission is done. Okay, emission is done, and I'm not going to go through all of this, but let's go into scattering, which is even more complicated. Okay, in scattering. Okay, so let's consider in scattering. Alright, so this is what actually makes radiation transfer equation complicated. But let's start breaking the problem down. Okay, so let me use this optical thickness diagram. I'll just paste it where this where this is, as a comparison why this optical thickness thing is important. But we'll consider scattering now. Okay, so again, let's go back to our little diagram, and we'll have some area here. Okay, and I'll draw a small box. Okay, relatively small relatively speaking. So again, this box will have a certain ds. Of course, if you want to use optical thickness, we can use d tau instead, d tau lambda, but I'll use ds for now. We can convert it to d tau lambda later. This will have a certain area, dA, and then it will have some sort of intensity coming in, I lambda. Okay, at S, and again I lambda, S plus ds. Alright, this is the basic picture of what's going on. So I'm just going to copy and paste. Maybe I'll use this template a lot. Right, so I can just paste it back into Paint anytime I want. Now let's consider the effect of what do you call that? let's say we have radiation coming in. Okay, again, it's I lambda, but it's going at some direction j, and it happens to be scattered into this direction. So how do we start mathematically formulating things? So let's take a look at the textbook. Okay, so what they have started to do is an energy balance. Okay, an energy balance. All right, so let's do an energy balance. Okay, so we have to do it slowly. So in scattering, we can start by doing an energy balance. All right, so again, we can do this dids, or rather we'll not do dids. We'll start from the very basics. All right, let's start from what intensity is, because there's lots of things coming in, such as the normal area, power per unit normal area per unit solid angle, right? So intensity is power per unit normal area multiplied by solid angle. Okay, so what is the energy being contributed to by I lambda? I lambda. Okay, so energy being contributed to, or power contributed to, let's use the correct word, power contributed to by I lambda is equals to I lambda times dA times the solid angle d omega. Okay, so I'm not considering anything else here, but just this little pencil of rays coming in here. Okay, and likewise for the rays exiting, I'm only considering this small little pencil of rays around in this direction, right? So power contributed to by, this is I lambda at S, and this is I lambda at S plus ds. So we have I lambda S plus ds dA d, okay, omega. So this is the energy power coming into the system due to this I lambda. This is the power exiting the system due to this I lambda at S plus ds. Okay, so that's just a simple energy balance. Then what is the power contributed to by this third ray? Right, to the system by the third ray. So yeah, what is the power contributed to? I lambda. So let's just for now put it as J, and I'll stop the video here because we're about to reach 20 minutes. See you guys in the next video where we'll continue talking about this in-scattering phenomena. Let's see you guys next time.